Hello, welcome to this new edition of InSite Bytes. Today we're going to have a look at how can we calculate source mechanisms when we have data, seismic data that has been recorded using triaxial instruments. One of the ways to characterize our seismic source is using the moment tensor inversion, as it's shown by this equation, which basically what it's showing us is that what we see, which is on the left term of this equation, that we record on our seismogram displacements, it's a result of the convolution of our seismic source given by this list of moments and the green function, that it's the medium that our waveform has been traveling through. So if we have this as an input, and if we know the green function, then we can solve the equation and obtain the moments that will characterize our source. In the case of InSite, well, the inversion is performed using a single value decomposition. And as it says there, we need a minimum of 6 displacements on the left-hand side of this equation to get a solution, basically, for our 6 independent moments. If we have more, much better, because our equation will be overdetermined and will be more robust. We will get a more robust solution and more uniquely defined solution. And this is just a visualization of the meaning of these terms that we've seen there, called as moments. This is the moment tensor. And we can see it's symmetric. It's a symmetric matrix, and it has 9 elementary couples, basically. And we can reproduce any seismic source by a combination of these 9 elementary couples. The meaning of each of these is just the moment. For example, if we take this term, the moment 2, 3, will be the forces acting on the x3 axis, in this case the vertical axis, in the direction of x2. And so here we can see what we have in the diagonal. There's no moment in them, basically there's no torque, because the forces are in the same direction as the axis that they are acting on. Right, and what do we get in InSite? After this is all done in the background, the calculation of this moment tensor. What InSite will give us is a solution for it, and the solution comes as a series of what would be the eigenvalues of this inversion, each of them representing one of the axes that are displayed here in our beach ball. And the normal to this axis would be interpreted as the fault plane. We also have in InSite the option to display them as in a TK plot. The TK plot, basically, it's by T we mean the deviatory component, K is the isotropic component of our moment tensor. So by calculating the value of the deviatoric and isotropic components, our event will fall in one of the spots in this plot. And this is useful to analyze a full data set, basically, and see how our source mechanism changes over the fracturing process. In the center of this graph, we will have the typical lower couple events. So, before moving on, just for a bit more of analysis, let's go into InSite. And here we have a catalog, a process data. It's not a catalog, it's actually a data set of 500 events that were induced. I'm going to have a look in the 3D visualizer. Were induced during the hydraulic fracturing of tight gas formation, and they were monitored using a string of 12 downhole geophones, triaxial geophones in this case. So what do we need to do to calculate the source mechanism for them? Well, we need to first go into this tab in our processing settings in the mechanism tab and select the amplitudes that we want to use in our inversion. So we have in this case the option to use only the P wave, the rotated P wave, or if we can pick them as well, use as much information as we have, in this case the SH and SV components of our rotated trace. If we were working with uniaxial instruments, these options would not be available, and we would only have the option to work with whatever, with the uniaxial data, in that case P wave uniaxial amplitude. Right, so once we have configured that, we need to go to our waveforms, have a look at our waveforms. For example, this event, we have the P wave arrival and the S wave arrival. We need to pick separately the amplitude and for the P wave and the SH and SV, because that's what we're going to use in this case. To do so, we double click on one of them, to get a view of the 3 channels. I'm going to go back to the top instrument, and we enter, well, it's the triaxial view that we saw before, right? Once we are here, we need to make sure that we are displaying the rotated waveform, and rotated in this case to the into the P direction, the direction of the P wave, and direction of the SH and SV components. And the algorithm we're going to use in this case for the rotation will be an event-defined rotation. And it's very simple. We might need to zoom in a little into our trace. We right-click and we have the option to add our rotated amplitude peak. In this case, the pink line, pink cursor is used for the P wave. If we go to the next window, which is oriented along the SH, we have here the option to pick the SH amplitude. And also similarly for the SV amplitude. Right, and we need to do this for all of our instruments. We don't need to do this manually. It's recommended because this is quite sometimes quite subjective, the way you select the position to measure your amplitude, which is different to the position where you measure your arrival. But there are ways to, it's also possible to automate this if we are happy and we think we have a good quality data. We can automate the process by selecting this option that we have here at the bottom, is auto pick PSH and SV amplitudes. We add it and then we can just run it and it will be automated. At this point in here, it requires first, of course, the location. If our event is not located, it's not possible to rotate it either. So we wouldn't get these rotated PSH and SV amplitudes. Right, so going back to my waveform that we have picked that manually, and it's just a matter of simply perform the source mechanism inversion. We have here the window that informs of all the steps that it's been taken. Basically, it tells us what is the whole information that our input, basically, what will be the phases that we're using for each of the instruments, what is the raw amplitude. The corrected amplitude is corrected to distance, basically, distance and azimuth to our sensor. So you can see that's the input that we have. And this is our inverted moment tensor. It's a very quick process. It's just single value decomposition basically. And this is just giving us an idea of the covariance matrix, the orientation of the eigenvectors and how they are interpreted as with the pressure, the null, and the tension axis. That would be the minimum, medium, and maximum eigenvalues. And also an information about the different components, the isotropic, the double couple, and the compensating linear vector dipole components, also decomposed as purely isotropic, the percentage of isotropic, and the TK, the deviatoric and isotropic components that will help us to get the display in the TK plot. And of course, yeah, the corresponding fault planes. We have two possible solutions for the fault plane. That's it. And yeah, we can go and visualize our mechanism. And we can see here our coverage is not great. Basically, we're looking from one angle. So it's not ideal for what would be the fault plane inversion based on purely on the amplitudes, but it's more robust for the moment tensor. So yeah, we have a good quality in general for the moment tensor, and we can have a look at it in the TK plot. And we have here our event, how it falls, quite close to being a double couple component with, yeah, close to the center. The density plane here shows the results for all the other events in this data set, all the other enable events in this data set. If we check on the visualizer, we can also display all of them. We can display all the enable events. If we want, we can scale them to time, and we can analyze how our fracture mode, our source mechanism, has changed in time, etc. Okay, so I hope this quick overview on how to calculate source mechanism for using triaxial instruments is used in InSite. As always, if you have any questions, please don't hesitate to contact us in applied.seismology.co.uk. And we're looking forward to seeing you in the next edition of InSite Bytes. Thank you for your time.